Hi everyone, welcome back to chemistry. In this video, we're going to start chapter 2, which is all about elements, atoms, and the periodic table. So let's go ahead and talk about elements first. So remember from last week that an element, we said, is a substance that can't be broken down into simpler chemical substances. So examples of some elements are, hydrogen or helium or oxygen. Anything that you find on the periodic table of elements is an element, right? And there are about 90 naturally occurring elements that are known on Earth, but scientists have actually been able to create additional elements that don't naturally occur. And this is just using different technology. So today, we actually recognize 118 elements. So if you look at a periodic table and it doesn't have 118 elements on it, that just probably means that it was a little bit of an older periodic table. All right, so all of the elements on the periodic table, they have different names, and those names come from all kinds of different things like planets, mythological figures, geographic locations, some of the people who discovered them, famous scientists and stuff like that. So I think that's pretty cool. In addition to the kind of longhand name, right, something like writing out oxygen, we can also abbreviate it just to make our lives a little bit easier. And those abbreviations for each element are called symbols or chemical symbols. And each element has one. And they're very important to get correct. So you want to make sure that you're writing them exactly how you see them on the periodic table. By convention, the first letter of the chemical symbol is a capital letter, while the second letter, if there is one, not all of them have one, right, like oxygen or fluorine, but if there is a second letter, it's always going to be in lowercase, like you see with neon here. All right, and this is really important. So I want you to try to get the hang of this. So let's go ahead and try this out. So use your periodic table to find the correct symbol for each element, and then come back and we'll discuss it. Aluminum here, what'd you guys put for that? I got capital A, lowercase l. Iron is a little different. That's capital F, lowercase e. That one might have taken you a little bit of time to find because it's not super intuitive. And that's because it was originally in Latin. Okay, so it kind of, the name carried over from Latin, which is really cool, I think. What about gold? Yeah, gold is AU. Another Latin one. And then mercury. Yeah, mercury is HG. Oops. HG. All right, so we also talked about atoms last week, and we said that atoms are the smallest part of an element that maintains the identity of that element. And atomic theory is the scientific theory that matter is composed of these tiny, tiny, tiny particles called atoms. And John Dalton gets credited with coming up with, modern atomic theory a lot. He was an English chemist in around 1803. But these individual atoms are so, so, so small that even the largest atom has an approximate diameter of only 5.4 times 10 to the negative 10 meters. That is extremely tiny. So most elements in their pure form exist as just individual atoms. So things like lithium and sodium and magnesium and carbon, they just exist of individual atoms of those elements. But some elements in their naturally occurring state, they actually like to bond to themselves. So there are 7 elements that exist as diatomic molecules just in nature, in their natural state, and that's given by the mnemonic Hofbrinkel. I know it sounds a little weird, but it does kind of stick in your brain, maybe because it sounds so weird. So Hofbrinkel, so that stands for hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, and chlorine. So hydrogen's kind of the odd one out over here, but the rest form this little 7 on the periodic table, which is pretty nifty because there are 7 diatomic molecules. So you do have to memorize that hydrogen is one of them as well, because there is hydrogen's kind of on its own over there. But it is kind of cool to be able to draw that 7 over there. So this is something that you do need to memorize. So what about the structure of atoms? So atoms are made of 3 subatomic particles. So subatomic meaning smaller, smaller than atoms, right? Subatomic particles, protons, neutrons, and electrons. So the first subatomic particle that was found was the electron. The electron is very, very, very here's the mass right here. It's about 9.109 times 10 to the negative 31 kilograms. That is so, so small. But it was determined with experiments that the electron actually has this negative electrical charge. So even though it's really tiny, it has this charge that we'll find in the future in this class makes a huge difference in how things react with each other. By 1920, there was some evidence that indicated that there might exist some second particle, and we found that it was a proton, which has a mass of 1.67 times 10 to the negative 27 kilograms. So what you'll notice is that protons are actually more massive than electrons. So if you look at those two exponents there, you'll notice that negative 31 is smaller than negative 27. So protons are larger than electrons. And they also have the opposite charge of an electron. So electrons are negative and protons are positive. And these protons and electrons, because of their difference in charge, they're attracted to each other. So think of the term opposites attract. And that might help you memorize that. You could also think of it as a magnet, right? If you put 2 of the same side of your magnet together, it's going to repel. But if you put the opposite sides of your magnets together, they're going to attract each other. And then in 1932, we also recognized the existence of the neutron, which is a particle that has the same mass as a proton, but it's neutral in charge. So it has no charge. And it turns out that the protons and neutrons kind of hang out in this little clump in the middle of the atom, and that's called the nucleus. And then you'll notice a question I have here. How did scientists discover the nucleus? I'd urge you to look up, if you're curious, the Rutherford gold foil experiment. So electrons are actually outside the nucleus. You can see them here, kind of orbiting around the nucleus because they're attracted to the positive charge that's in the nucleus. So remember, why is the nucleus positive? Well, remember, the nucleus consists of protons and neutrons. If protons have a positive charge and neutrons have no charge, then the overall charge in the nucleus is going to be positive, right? So the electrons are attracted to that positive charge, and that's what keeps them orbiting around like that. But remember, I said that electrons are really, really, really tiny, and that protons and neutrons are around the same mass as each other. So most of the mass, in fact, almost all of it, of an atom is located in the nucleus. Electrons are still really important, though. They actually account for the atom's size because they're orbiting around that nucleus, and that's what's creating that size of that atom. And we'll talk a little bit more about that in the future. So let's do a quick summary of these subatomic particles because I know that's quite a bit of information. So just to recap, protons and neutrons are located inside the nucleus, and electrons are orbiting around the nucleus, like so. We talked about protons, neutrons, and electrons. Each of those particles, they actually have symbols. So instead of writing out proton every time, scientists will often abbreviate the proton as P plus, right? Why the plus sign? Yeah, because protons are positive, right? We have the mass here, but we can also think of the relative mass. And what that means is, right, in terms of all of the other parts of our atom, how much is a proton kind of contributing to the mass of that atom? So in this case, you'll notice that for protons and neutrons, the relative mass is 1. Whereas for electrons, the relative mass is 0.00055. That's a lot lower, right? So that's why we always say that what accounts for the mass of an atom is really just the protons and neutrons. This number is so small that we really kind of just negate it. Okay, but it is there. Electrons are there. And the charge is really important as well. So electrons, we said, have a negative charge, specifically a -1 charge. Protons have a +1 charge, the opposite of electrons. Okay, and then we said that neutrons are neutral. They have no charge. Neutron, neutral, right? So again, my kind of way of memorizing this when I first started out was thinking about protons as positive because of that P there, neutrons as neutral because of that NEUTR there, and electrons are just whatever's left over. But hopefully this summary helps. If it doesn't, or if you have any other questions, please don't hesitate to let me know, and I'll see you in the next video.